Hi, and welcome to this introduction to integration. Just wanting to give you a kind of big picture view of what's going to be happening in this chapter. So to start, I want to remind you about where we've been. So there are two really big ideas in calculus. And one of the big ideas is this idea of instantaneous rate of change. And we saw that in terms of instantaneous velocity. We saw it when we were thinking about the slope of the tangent line, which we were able to compute using the derivative. Now in chapter 3, we're going to encounter in detail the second big idea, and that big idea is this sort of accumulated total idea. How do you compute the accumulated total? And in geometric terms, that can be thought of as the area under the curve. So you hear a lot of talk about area under the curve in this section. Now, unfortunately, for a lot of curves, like this one that's shown here, you don't have a nice geometric formula to find that area, like you do, say, area of a triangle, area of a rectangle, area of a circle, all those things you have nice geometry for. What we're going to do instead at first is approximate the area. And how that's going to be done is by drawing rectangles, because rectangles are really easy to compute the area of, right? Length times width. So what I've done in this example is I've drawn these three rectangles, and on each one you go up to the curve and then make a little rectangle that's that height. These are done with the left sides matching. So I have these rectangles and they approximate the area under the curve. If I made more but smaller rectangles, I would get a better approximation. And then I'll take the limit as n goes to infinity, where n's the number of rectangles, and I'll end up with the actual area under the curve. Now I want to introduce you to the two different notations that you're going to see a lot of in this chapter. So here on the left, we have the notation that corresponds to what I've been talking about so far. So this thing is the symbol for the net signed area under your function f of x. And these little a and b here tell you that your x values are going to go from a to b as you're thinking about the area. And this is called the definite integral. And when you compute one, you should come up with a number. And by the way, this funny symbol here, the integral sign, is supposed to remind you of an S that's kind of been like stretched out because we're summing up all these areas of little rectangles. So S for sum, but stretched out. All right. Meanwhile, on the right-hand side, something that looks very similar, only with no decorations, no A or B. And this thing is called the indefinite integral. And you compute that by taking an antiderivative of the function f. That means finding a function whose derivative is f, or undifferentiating. And when you do one of these, you should come up with a function rather than a number. And it's sort of annoying at first that we have these two things and they seem like they're different. One gives a number, one gives a function. One talks about area, one talks about undifferentiating. And they have basically the same symbol. And you might think that's really just kind of playing fast and loose with the symbols. And I just want to reassure you that it's not. I like to think of it, it's sort of like butter and peanut butter, because in some sense, butter and peanut butter are nothing alike, right? Butter is like you take this animal product, cream, and you shake it until it turns into a solid butter. Versus peanut butter, you take plant product, nuts, and you grind it until it becomes smooth and creamy. So it seems like those two things are very different, but when you think about what you actually have when you're done with them, well, butter and peanut butter, they're both kind of similar. You can spread them on bread, they have that same texture, whatever. So I promise that using this very similar notation for those two different things is justifiable and reasonable. And you'll see that in the next section when we come to the fundamental theorem of calculus. So what does this theorem say? It says, look, if you are trying to compute the area under the curve, you can actually do it by undifferentiating, because this function capital F is somebody whose derivative is the left, and taking the difference. So the moral here of the fundamental theorem of calculus, you can actually compute that area by using antiderivatives. Here's another way to put the fundamental theorem of calculus. Could also think of it as saying this. The total change of my function as I go from A to B is basically what you get if you add up all the rates of change as you go along. So like add up a bunch of little changes to get to the big change. And when you put it that way, maybe it's not quite so surprising. You're going to see this in a lot of applications in this chapter. So if your original function is telling you velocity, for example, so that's the velocity is the change in position. So you add up a bunch of changes in position, you get displacement or distance. If you instead started with acceleration, acceleration is the rate of change of velocity. So the changes in velocity add up to the total change in which is the velocity. Okay. We also have in sort of a business concept, you might think about marginal cost. So the changes in cost to produce one more. And if you add up all the changes to produce one more and then to produce the next one more and the next one more, you're going to end up with the total cost to produce all those items. Or as a really different example, but still kind of businessy, you have a function that tells you the number of telephone calls you had at each minute X throughout the day, and then you kind of added all those up, think about those rectangles again, you would end up with the total number of phone calls during all the hours that you were adding up across, like maybe the whole day.